this is the idea of the proof behind the intersection of a finite number of open sets is open. So very first, we have to think about what it means for it to be an open set. A set is open, and I'll draw this in 2 dimensions because it's conceptually maybe a little bit easier. If whenever you pick a point, you can always find an epsilon ball small enough, I'll make it red, that you can completely draw it around there. So I'm going to be drawing in 2 dimensions because it's a little bit easier to draw. But really, in 2 dimensions, this would have to be a perfect circle of radius epsilon where the center is that point. Really, what we're talking about in this class lies along the line. So what that means is we have to draw a little epsilon ball. That's just an interval, right? A minus epsilon, A plus epsilon. Okay, but we're looking at a finite number of open sets, and we're going to intersect them. So I'm going to get to the proof here, and we'll just remember what it means to be an open set. Well, I'm going to draw a Venn diagram. Here's one open set. Here's another open set. Here's another open set. Now, like I said, this is in 2 dimensions to conceptually show you what's going on. So this is O1, that's O2, and this is O3 down here. And they have kind of a common intersection. And we want to look at this intersection in the middle, which maybe I should outline in, let's outline this one in red. We want to see, we just want to look at this part right here. This is going to get messy here in the middle, but it'll be fine. You'll be able to cope. Okay, right, so we want to figure out if this intersection is open. How can you tell if something's open? Well, you need to be able to show that for any point in there, you can draw an epsilon ball that's small enough around it. You can draw an epsilon ball that's completely contained within it. You can't have an epsilon ball that looks something like that. You can't hang over outside the edge. That's bad. Bad. Don't do that. So what we're going to do is we're just going to pick any point. Now, I could clearly draw it, but we don't want to use just drawing it and that, especially since I'm not a very good artist. We want to rely on logic. So what can I know? I know that this point is in the intersection, so in particular it's in O1, which means that I can draw an epsilon ball around it that's completely contained in O1. Now, to draw an epsilon ball, I may or may not be able to do it, but what that means is that I should be able to draw a circle around this point where this is the center. So let's see if I can do this. No, obviously I can't. Let me just try to fix this up a little bit. Okay, let's try this again. So let me just draw. That's at least close, right? That's not very good. Our notation here is that this circle is V epsilon 1 of A. And this point here is A. I don't want to write it down there because it's going to get a jumbled mess in there. But here's an epsilon ball around it. O2 is going to have an epsilon ball such that the point is completely contained within an epsilon ball within O2. And that's going to be called V epsilon 2 of A. And that's going to be represented by a blue circle. Now, these are supposed to be perfect circles centered around A. So these should be concentric. Either the circle should be completely outside of the green, or it should be equal to the green, or it should be inside the green. They should be concentric. So notice it's completely possible that I could draw this. That's supposed to be circle, concentric. This blue circle is completely contained within O2, so that would be valid. So, but notice we have a little problem here because the green and the blue are not contained within the red. But I'm going to get saved by this last one. This last one is V epsilon 3 of A. Right? I need to be able to draw a circle that's completely contained within this mass right here. Well, notice it can't be outside the blue because the blue goes outside of O3 right there. It can't be outside the green because the green goes outside right there. So I need to be able to draw it like that. And notice that this is the smallest epsilon. Epsilon 3 works. Epsilon 3 shows both A belongs to O3 and A belongs to O1 intersect O2 intersect O3. That's the idea, is that they have to be concentric, and the smallest one is going to show that's in the intersection.